Welcome to part 2 of a walkthrough for the progress measures for Grokking via Mechanistic Interpretability paper.
You should go check out part 1 for a overview of what's interesting about the paper and how to think about it. Here we're going to be diving deeper into the weeds. We're going to spend a bunch of this focusing on what the algorithm the model learned to do modular addition actually is. And metaphorically, a lot of the vision of this paper is to beat a reader over the head with, yes, we really, really understand this one model, and it is possible to reverse engineer a model.
32 models. There are more models. There are more models in the appendix.
I do apologize. I interpreted one model. Lawrence interpreted 32 models. So Lawrence is 32 times better at reverse engineering than me. And you should go check them all in the appendix. I also have a coding tutorial where I just train a model to do modular addition and write the code to interpret it that you should go check out if you want a more hands-on thing. And also, if you find this work exciting and you want to go build on it, I have this sequence called 200 concrete open problems in Mechinterp with a section on algorithmic problems like this and a section on understanding training dynamics like Grokking that you should go check out, since there are just so many things that we can do with reverse engineering networks and so few people working on it, and it is terrible. Let's jump in. It's pretty important to get at a high level, get your head around what exactly is the algorithm the model has learned and how it fits into the model. So at a high level, modular addition is equivalent to rotation around the unit circle. You can think of the number a as the rotation go around the circle by a nths. Here, n is 113. You can also think of it as go around the circle with a times w, where w is some multiple of a 113th of a full term. Think of the input b also like that. Add them together to get a plus b, or rather compose the rotations to get the sum a plus b. This is instantly mod 113 because the k over 113 just goes around the circle and it's just fine. And then a weird thing about the model producing the correct output is that it produces 113 logits. These go through a softmax to get a probability distribution. You can kind of think of a softmax as just an argmax. It just finds the biggest logits and says, okay, that one's the right answer for our purposes. And for the cth output logits, it learns to rotate backwards by c to get the rotation a plus b minus c. And it said, okay, how can I tell if this is the do nothing rotation? Oh, I can look at the x-axis. That's biggest for c equals a plus b mod 113. And so it kind of works. And in terms of how this translates into the model, so transformers are made up of these this is a one-layer transformer, which is transformers on easy mode. And it's made up of these 4 layers. You start with the tokens, which are just these integers, just 0 to 112. And there's an embedding. The embedding is basically a lookup table that just memorizes for each possible input number a vector in what's called the residual stream, which is like the internal space of the transformer. This is just an arbitrary lookup table. And it decides it's going to memorize that each number a maps to sine WA and cos WA for this angle W that is some multiple of 113th of a way around the circle. And this is actually really easy. Models can memorize whatever function they want. They could, I don't know, memorize the busy beaver number mod 113. That's also a perfectly reasonable thing it could memorize, or some crap like that.
Okay, well, I mean, it can't represent it.
Yeah, it's a lookup table.
Oh, sorry, mod 113, you said. Yeah, absolutely. The mod 113 is fine. That's the important part.
It's being converted to a vector. It could, in theory, represent that, so long as you allow it to have enormous weight. Though that's a silly example.
Oh, God.
Yeah. But it can represent lots of crap.
I'm pretty sure Float 32 won't like that.
Fair point. Then there are these attention layers and MLP layers. For our purposes, the key things are, so the model's input looks like number A, number B, special equal sign token. The attention heads move the values of A and B to the residual stream on the equal sign token, because transformers have a separate representation per input. And it's made up of these 4 heads that all act independently and in parallel. And the main purpose they serve is just moving things to the correct position. So they also partially do this kind of combining A and B into A plus B.
Also in our network, 2 of the heads decided to, instead of doing multiplication, they instead amplify the size of the embedding to get around the weight norm restriction. It was great.
I mean, the other 2 probably also do this a bit and also do some multiplication, I'm guessing.
I mean, the other 2 seem to do much more multiplication. This is the classic, why is it so hard to interpret these 2 heads? And then, why is it that when you add together their attention patterns, it sums to 1? And you're like, oh, I see what it's doing. That sort of thing.
I love it. Wait, it adds to 1. That's beautiful.
Yeah, it does. It does. It does. If you look at, I mean, it kind of makes sense, right? If you look at
We'll get to this later. 2 in the weeds.
We'll get into that later. Yeah.
The key thing is that there are these layers, they do internal processing. The important bit is the MLPs, where there's just a linear map from the residual stream to 500 neurons, each of which has their own relo activations. You map them back. There are these skip connections, which for our purposes mostly don't matter. And you can ablate them, and it's kind of...
Wait. The first one matters a lot. The one around the MLP doesn't matter.
Wait, the first one matters a lot?
It matters a lot, yeah.
Wild. Okay, we'll get to this later. The important thing for the high-level algorithm is that the model learns to convert these like memorized lookup table of like sine and cos WA, which represents the rotation, sine and cos A, and then it learns to compose them to get A plus B using, of all things, trig identities. There's 2 kinds of things in a model. There's activations, which are functions of the inputs that are calculated at inference time, and there's parameters, which are just like learned numbers that are part of the model's function. The core operations in the model are matrix multipliers of activations with parameters. And so it's really natural for a model to add activations together. It's really natural for it to multiply activations by parameters. It's kind of weird for it to multiply an activation by an activation. And it's very natural for it to learn a lookup table, because that's what an embedding does. So it learns a lookup table to get the trig things. It then learns to multiply 2 activations, which is weird and hard. And it's simultaneously done by the MLP relo activations and by the attention head patterns in a way that's messy and we'll get into. And then adding them together is easy. And then it maps these to the output logits via this final linear map. And this is multiplying this activation, cos WA plus B, by this parameter, cos WC, because there's a fixed set of parameters for each output logit, and this is easy. And so this bit turns out to be what the network spends by far the most effort doing. And also, these 2 steps are like much easier to just read off from the weights, because it just learns parameters that does them. I think it's also worth just dwelling a bit on kind of on a meta level. Why did it learn this algorithm? There's something I find kind of cute and satisfying, intellectually satisfying about Mech-Interp, where models are kind of these weird alien organisms. They're learning to do computation. They're often learning tasks that like a human could do. But the thing that's natural for them to express internally is very different. But it kind of makes sense if you stare at it hard. And inside a model, matrices and linear algebra is its natural language. And so thinking of these kind of discrete numbers as rotations around a unit circle and like a geometric transformation of space that can be represented by a matrix is extremely natural. And then like composing them and mapping them to a thing where an argmax figures out the right answer is like extremely natural. Even up to me, this is like really, really weird. And I only figured this out by like a lot of time staring at the weights and playing with the model. It's also worth emphasizing, since people sometimes confuse this point, that like I did not come up with this algorithm in advance. I did not train a model to do this. This is pure post hoc interpretability, where it turned out to be really weird, and I stared at it really hard, and we managed to figure out what was going on. Just to recap the high level of the algorithm, lookup table mapping A and B to these trig terms, MLP activations and a bit of attention, multiplying them to get A plus B. And then neuron to logit map converts them to cos W A plus B minus C, and the softmax just looks up the correct C. Staring at the weird alien language inside the models. It's so fun. Would highly recommend. How do we know this? So blah 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 related work, blah 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 setup, random technical details. As we trained this model on 30% of the data, we used full batch gradient descent. We used weight decay with a really big parameter of 1, and it had 500 neurons. And we did not use layer norm, and we did not tie our embed and unembed matrices. Go read the paper if you want the details. You don't need to understand what any of that meant. The key parameters and things we're going to look at are, we're going to look at the activations of what the embedding learns, what the attention patterns are, what the MLP neuron activations are, and the output logits, which is argued in a bunch of places, including a mathematical framework for transformer circuits, which I also have a walkthrough on, are kind of the reasonable things in a model to try to interpret, and that most other things are kind of weird and arbitrary. And we're going to focus on the weight matrices of the embedding matrix, which represents this lookup table, and the map from the MLP activations to the output logits, which is actually this kind of factored linear map. WL equals the output map, the like neuron to residual stream map times the residual stream to output logic map. But turns out for our purposes, this is like the interesting thing to study. So we've got these 4 lines of evidence as nicely clarified by Lawrence from my original massive clusterfuck. And so there's these 4 things. There's weird coincidences of periodic structure. We just like look inside the model and it's just really periodic. And it's like, what? Then we can look at the actual mechanisms implemented by WL, the neuron logic map. Do we look at the embedding here, or is that in a different section?
The embedding's in periodic structure, actually.
Cool. Okay. So in the periodic structure, we also look at how you can just read off the lookup table, mapping the inputs to the trig things in the embedding. Then in this one, we can just look at the neuron logic map and just read off, okay, this is learned cos WC and sin WC, and it aligns with the cos W A plus B terms we expect. Then the third line of evidence, we look at specific neurons, and we see that the neurons represent these cos W A plus B and sin W A plus B terms, though with like some other stuff. And also the wild thing that the neurons kind of cluster into different frequencies. And finally, we use ablations to verify that we aren't like lying to ourselves by just deleting loads of stuff that our algorithm says shouldn't matter and showing that it doesn't matter, and deleting stuff our algorithm says should matter and showing it breaks everything.
Right, exactly.
Oh yeah, we should probably explain the idea of key frequencies.
Yeah, absolutely. This particular mainline model uses 5 different, represents 5 different frequencies in the sense that it picks cosine of 2k pi over px, or sine of 2k pi over px as its computation. But here, k is the frequency. And in fact, it uses 5 frequencies listed on the right over here, 14, 35, 41, 42, 52.
Note, these are completely arbitrary, and we found no structure in which ones it learns.
Yeah, they're completely arbitrary, and there's good reason to expect them to be arbitrary because p is a prime here. So there's some sense in which all of these are equivalent. What matters for the network, though, is that it learns sufficiently many of them, because what you observe is that cosine of 14 is very, very close to 1 at 8, and it's equal to 1 at 0. Right, so this this topmost line, this smooth, very small line, very slowly changing line, it's exactly 1 at 0 because cosine of w0 is always 1 for any w. But then if you scroll over to 8, you'll see that it's also very, very high at 8. So if the network just used a single frequency, cosine 14 or whatever, what you'll see is that the network would assign very high logits to some answers which are equal to 8 mod 113. And this is bad, right? The network is going to assign very high probability to things that it doesn't want to assign high probability to. So instead, what the network does is it adds together a bunch of other frequencies. So this dashed black line is the sum of all 5 frequencies, and you can see that over here, it is actually much, much larger at x equals 0 than it is at any other x.
And the model learns kind of separate but equivalent circuits that are all acting in parallel that kind of combine to constructively interfere at 0 and destructively interfere everywhere else. Note that the model only cares about what happens at like 0, 1, 2, 3, 4, because the inputs are discrete, which is also why the frequencies don't matter. Like, from the perspective of the model, because you're only taking these snapshots, it turns out you can just permute the inputs and outputs so that cos 14x looks the same as cos x. Also, we're going to refer to w equals 14 times 2 pi over 113 as cos 14 because nobody got time for that.
We do not want to say 2k pi over p over and over again.
God, we have so many figures. We're going back to the weird, surprising periodicity section. We can just look at the embedding matrix. The embedding matrix is this lookup table mapping. It's like a 113 by 128 matrix, input vocab by residual stream. And you can do this thing called a discrete Fourier transform on it, on the vocab dimension, to instead convert it into a lookup table for sine 14x and cos 14x. Or rather, for every frequency, you get to look up kind of what that maps to in the residual stream. And it turns out that a few of these are big, most are tiny. And here we've got a bar chart where this is sine 14 and cos 14, 31, 35, 41, 42, 52. Exact numbers, kind of arbitrary. But you can just like look at the embedding and it's like, okay, obviously this is doing something trig-based. There is no way this would learn something like that. If you look at like an arbitrary model or do an arbitrary rotation, this is like basically flat. And if you look at the WL, the neuron logic map, and do the same thing, this time it's a neuron, so 512 by output vocab 113 matrix. And we can do the Fourier transform on the output vocab side. And we can again see it's like a little bit less flat, but there are these 5 spikes. For some reason, the model also learns, I think, 30 or 31, even though it's not used later and doesn't appear in the output logits. I have no idea why. Plausibly, this is just some kind of weird vestigial organ that it learned early in training that it kept around.
Maybe if you trade it for another 100,000 epochs, it'll go away.
Yeah, that actually was this wild thing where if you keep training it, it's grokked by epoch like 15,000. But if you keep training it to epoch 43,000, there's like a tiny phase change where the model goes from purely attending from the equal sign to the A and B inputs to attending a decent chunk to the equal sign. And it actually slightly increases test loss and slightly decreases train loss. I decided I was going to be a competent, mature researcher and prioritize and not try to figure out what's going on there, and instead write up the paper. So that's surprising thing 1. Surprising thing 2 is that if you just look at the heat maps, so a nice thing about this problem is that we know the full universe of data. There's 113 A's, 113 B's. So we can just plot a heat map. For every kind of number inside the network, we can just take that number and we can, like a single scalar, take its value for all 113 squared inputs and plot it at the heat map. And if we do this for basically any of the things I said at the start should be interpretable, that is attention head patterns and neuron patterns, like neuron activations, they just look really periodic, like watts and like watts. Note that the neuron looks weirder because neurons are forced to be positive, so it can't quite do the like perfect periodic thing.
I mean, attention scores are also forced to be between 0 and 1, right?
Okay, this is fair. Turns out in practice, the attention scores learn to be 0.5 plus like a kind of small norm periodic thing. If you actually look at what these represent, actually, we'll get to that later. One interesting thing is the attention heads purely have terms of the form cos WA or cos WB, but not cos WA times cos WB, while neurons have all of them. And the final thing is we can look at the norm of the logits in the 2D Fourier basis, which is a mouthful of jargon, but basically means you can think of the logits as this kind of A by B by C tensor, where for every triple ABC, it's got a number. You can like rewrite this as a sum of, rather than like all possible pairs A and B, you can do it in terms of all trig functions A and B, where like cos 14a times cos 27b is just a valid trig function.
I mean, it's just a change of basis, right?
Yeah, it's just a change of basis. Everything's really nice. Turns out that these are an orthonormal basis, so everything's a rotation and it's lovely. You don't need to follow that. And it turns out if you do this, that the logits are just these 5 2x2 squares that represent them, and basically everything else doesn't matter. Everything is weird. Note that these are 2x2 squares that all have about the same number, not 1x1 squares.
If you look at the appendix, we show the patterns for way more heads and way more neurons, and it is consistently, see, right? All of them are periodic. Yep, there we go. That's the neurons.
I had a lot of fun figuring out how to use Plotly competently, and also figuring out how to export graphics that weren't terrible when you zoomed in on them. So, category 2, we can just read off the algorithm from the weights. So, if we refer back to the main algorithm figure, we assert that in the kind of from the neurons to the output logits, things look like this. The neurons have calculated these activations, cos WA plus B, and then there's the map, cos WC. And we saw that when we looked at the neuron logic map, most of it was consisting of these cos WC, sin WC terms. And each of these corresponds to a direction in neuron space. And this direction in neuron space, if you dot this with the actual neurons, it just gives you a number for each input A and B and each kind of trig component cos WC and sin WC. This table just shows the actual numbers you get when you do this. And it turns out that the cos 14c thing basically just connects to a cos 14a plus b thing, with the fraction of errors explained as 93.93% when you, I think when you remove constants, or is this without even removing constants?
Oh, this is with constants removed. We normalize the thing to be mean 0. Yep.
Great. And yeah, these are just like ridiculously high numbers. And this is just not the kind of thing you expect to see with coincidence.
Well, I mean, this is fraction of variance explained, so it doesn't actually matter.
Yeah. Variance is like when squared distance from the mean, so who cares?
Yeah, so you already subtracted the mean anyways.
Yeah, so what we have is just, okay, the logits are dominated by these 10 directions. When we look up the directions, they're just cos WC times cos WA plus B. It's just exactly what we would have predicted. And you can just look at the logits, and the logits are just really well approximated by this. It's like 95% of the variance. And this is just kind of wild, because the logits are this A by B by C tensor, 113 by 113 by 113. What we're doing here is we're flattening it to this 1.4 million dimensional vector, comparing that to what we predict should happen with this like 5-dimensional thing. And it explains 95% of the variance. And it's like, yes, we obviously understand what's going on.
I personally find this evidence the coolest. Like the fact that our neuron logic map, we can approximate of 10 directions, which is like kind of cool. But the fact that when you like take each of these directions, you can read off the trig identities that the MLP layer is computing. I think this is pretty cool. I know Neil thinks this is less cool than I do, but I like table 1 a lot.
I think it's cool. I think that the logits are well approximated. Just like you can predict a rank 5 subspace of 1.4 million dimensional space. This feels like the best evidence.
But like we're doing zero ablation basically, right? Like, and then all right, anyways, we don't have to get into nitpicks of different styles of ablations.
It's fine. We've got more than enough evidence to go around. Cool. So that's the first half of the evidence. Next bit is this zooming in, approximating neurons with sines and cosines. Want to take this one, Lawrence?
Yeah, of course. So, in the previous thing, we talked about how, like, first of all, the neuron logic map WL, that reads off trig identities from the MLP layer, which is calling that M or MLP layer. In 4.3, we try to answer the question, like, how does the MLP layer actually represent the trig identities? So first of all, we show that 2 of the tangent heads compute like degree 2 polynomials of sines and cosines. So basically it takes, sine and cosine a particular frequency and multiplies them together. And then the other 2 heads increase the magnitude of input embeddings in the original scheme. And then most neurons are well approximated by degree 2 polynomials. In fact, degree 2 polynomials are a single frequency. And then the map from neurons to logits is also localized by frequency.
Yeah, just to clarify, degree 2 polynomial here just means it's like constant plus sine 14a, sine 14b, cos 14a, cos 14b, some coefficients. And then the degree 2 part means sine 14a times sine 14b, etc. for the other four combinations.
Exactly. Yep.
Figure 5 shows how good an approximation that is.
Right. So like for the vast majority of neurons, like you can just take a single frequency, like one out of the 5 frequencies, and then approximate it with a degree 2 polynomial of that frequency. And you can see that like the vast majority of them are well explained by a single polynomial of this form.
Yes, and it turns out if you dig into the ones that aren't well explained, they're also doing an interpretable thing that's also horrifying, though still clean, where they're what I call the always firing neurons. So ReLUs kind of they set negative things to 0, they set positive things to exactly what they were. If you just learn a really big positive bias on your ReLU, it's just always going to be positive. So it's just an identity. And the model just learns to have maybe 40 neurons that just act as identities. And then because the attention heads have calculated some multiplied stuff, it turns out that rather than just using the skip connection around the MLP layer, as God intended, to move the attention outputs to the logits, it also wants to use a couple of MLP neurons to boost things. But it doesn't want to use the ReLUs because the attention's already computed the degree 2 polynomial. So it just has like a side channel that's the identity. It's just what?
And it's really interesting because ablating these neurons does affect loss, while ablating like the skip connection around the MLP layer doesn't affect loss very much.
Yes. I mean, because they're being boosted, they're probably a lot bigger than the residual stream.
Exactly. Like the coefficients, if you look at table 1 again, right? Like the coefficients involved are like quite large. They're on the scale of like 40 or 50 or 60. Yeah, so it makes sense why like the MLP layer is so much bigger than the residual stream. Because when it gets the residual stream, it's of size like 1 or 2 or 3. By the time it gets out of the MLP, it's of size 40, 50, 60. Yeah.
Yes. And a thing worth tracking is just, wow, the model, this is just a really weird problem because weight decay is so high. And the only reason it groks is because of weight decay. So it's just conforming heavily to this constrained environment. Also, I should clarify, when I say you learn a really big bias, these models don't actually have biases because biases annoy me. But it learns like a big constant offset by using a bit of the model that like always is like on average always like significantly positive. And it's kind of a mess.
Do you think that's related to why two of the heads are just like add up to a constant? Or like just end
Uh,
up like taking the key frequencies and amplifying them?
no, that's probably just to do with the weight norm. Like it's using the value output part of the head to make things bigger, is my guess.
Mhm. That makes sense. Yeah.
Yeah, the thing that it's using as a constant is probably the embedding of the equal sign or the like positional embedding of that bit.
The embedding of the equal sign, that makes a lot of sense. Oh, did we talk about that? Like in our problem, the transformer looks at a sequence of length 3, where the first is A, the second is B, and the third is the equal sign.
Yes. Yeah, if you want the gory details, you should go check out my coding walkthrough. Currently, I want to just convey like what we know and like the details of why we know. Technical implementation details, meh.
There's a different video for that.
Yes, finally, we can just read off the like neuron logic weights again in the trig basis. And we see that for the neurons that cluster by frequency 14, is just, rather than being these 5 things, it's just sine 14, cos 14, basically the only thing that matters. The neuron outputs do contain significant bits that are like cos 14a plus like sine 14b and stuff like that, but mostly just because ReLUs are not designed to multiply things. And so the best way to do this is via that.
The poor model has to multiply things with ReLUs.
I don't claim to have fully reverse engineered the last details of how it uses ReLUs to multiply, but I found this whack identity where the ReLU of 1 plus like x plus y is approximately, well, like x and y are these kind of Gaussian mean 0 norm 1 things. The output of that is approximately like a half plus a half x plus a half y plus 0.37 xy or something ridiculous, because you can think of a ReLU as adding a kind of interaction term, but when the input is negative, the interaction term is positive. And when 1 plus x plus y is negative, x and y are very negative, so x, y is very positive. And this just turns out to basically work.
That'd be great, and it would explain what's going on, except there's no bias term in the ReLU. So then, that's what makes it really.
You don't need an explicit bias term. You just learn a significant constant in the model, and everything uses it.
But you can read, if you had the bias term, you could read off the bias term, you could read the identity, right? But now we're just like, where's the bias term? Somewhere in the model.
Yes. Possibly removing biases was a mistake, but we've interpreted the model, life is good. And actually, it would have been sensible in hindsight to just get rid of the attention layer entirely and just do an MLP, which is what we did in a follow-up paper, because ReLU's all you need.
Poor model. Doing so much multiplication with addition.
Yes, and I kind of want to just dwell a bit on the fact that the MLP neurons cluster by frequency. This is just really cool because one of the big open questions in actual language model mechanistic interpretability is, how do neurons work? Do models map specific features to specific neurons? Is it doing some polysemanticity where a neuron represents many features? Is it doing superposition where it's compressing more features than it has neurons? And here, things are very nicely aligned with neurons. And actually, neurons are kind of the opposite of superposed, because the degree 2 polynomial is just like a rank 9 subspace. There are 9 terms, the linear trig terms, the quadratic trig terms, and the constant, that explains, say, these 44 neurons, or 100 neurons in the bigger clusters. And the model decided to stress about because something weight decay.
Oh, I mean, it's also the attention heads, right? So when you take out the actual attention heads and you train your models on modular addition or group composition, you find many, many more frequencies than we see in this model.
My guess is that's because of whether the model has factored embeddings or not. A factored matrix is where rather than having just a input by output, you've got an input by middle, middle by output, and multiply them together. And for some reason, we found in some follow-up work that if you have an MLP with just an input map, ReLU output map, it learns all frequencies. Kind of because just each neuron is independent of every other neuron. Just because one neuron learns frequency 14 doesn't mean any other neuron cares about this. And you can use maybe 5 neurons to do an okay multiplication of the trig terms, or maybe 9. While if you've got a factored input to the MLP, for some reason this makes it prefer to learn kind of a small number of frequencies.
In particular, it's not just factored, it's factored through the attention heads, right? Of which we only use 4 or 2 or 8 or whatever, a much smaller number than the number of neurons. And I think it definitely has something to do with this.
So, I don't know, you've got the attention heads which amplify things. Those have a bottleneck dimension of 64. You can fit a lot of frequencies in 64 dimensions.
Okay, sure, but there's 2 of them that just do multiplication, right? And these 2, they can only do 1 frequency each. Anyways, that's really in the weeds. Yeah.
Yes. Finally, we've got these ablations. These are basically just sanity checking. You can look at the MLP neurons that are well approximated, and we can just say, let's literally replace them by this degree 2 polynomial. Loss goes from ridiculously tiny to 3% higher. Accuracy is unchanged, but this is kind of a meaningless statement because when you've got loss 2.5 times 10 to the minus 7, you have perfect accuracy, man. We can restrict neurons to just cos W A plus B and sin W A plus B and remove everything else. Loss is improved. Then we can ablate the logits, where we change the logits to only have these A plus B terms, which importantly is the A plus B terms are kind of 2 dimensions per frequency in 12,000 dimensional space. Want to explain what figure 6 does?
Right, so in figure 6, you can go to your MLP layer and you can start ablating frequencies in the sense of we could start deleting all the terms that correspond to frequency 1, frequency 2, frequency 3, frequency 4, and so forth. And then we could plot the loss after you've deleted that particular frequency. So over there on the right, we could see the original loss, which is what happens when you delete no frequencies, just let the network run as usual. Over here on the left, we could ablate every frequency from 1 all the way to 56. And the thing you do see is that, very clearly there are 5 frequencies which increase loss significantly. And they're the 5 key frequencies. It's incredibly obvious. I didn't even want to color it differently. But to make it even more clear, I've colored them red.
Yes, and to be clear, we're ablating 2 dimensions in the 12-dimensional space of like the A and B parts of the logits.
Yes. Yep. In the logit space. Yep.
Pretty compelling evidence to me. And finally, we look at, so we claim the neuron logic map is well approximated by these 10 directions. And we just ablate everything that isn't in those. And does performance go up?
It goes up. Loss decreases by half. And then if you project it onto the null space of the 10 directions, loss is worse than uniform, which is great. 0 ablations for the win, something. Yeah.
Yeah, 0 ablation just meaning set the stuff that doesn't matter to 0. I think we mostly do mean ablations because network often learns big bias terms.
I mean, we do both. I think I've tried 0 and mean ablations for almost everything. The results are broadly similar for 0 and mean ablations in the sense that the terms that don't matter, and the terms that matter do matter. You could also do resampling ablations, Redwood's favorite type of ablation, and the results just hold up across the board. So, they're not specific to the type of ablation we're performing.
Just to briefly outline what an ablation is, I can give a link to my Mechanistic Interpretability explainer for more info. But basically, the idea of an ablation is if part of the claims we're often making when interpreting models is some bits matter and many bits don't, like some directions matter. This is true, you should be able to delete the other directions. This is called an ablation. The subtlety is what it means to delete the direction, where the obvious thing is to set it to 0, which is 0 ablation, which is the main thing done here in the standard thing literature. Mean ablation is when you take the average across a bunch of data, in this case, the entire 113 squared possible inputs, and replace the directions you want to delete with that. This is useful because it preserves bias terms. The picture to have in your head is like, you've got a cluster of points around like 5. If you 0 ablate them, they go to 0. This maybe breaks the network for boring reasons. If you mean ablate them, they round to about 5. And a resample ablation is when you shuffle these across a bunch of data, where you copy in that direction from like a random other input. And the intuition behind this is that maybe mean ablations are unprincipled because the network expects things to have some nonlinear structure, like they're points spaced around the unit circle. The average is the origin. Maybe it expects things to have norm 1 and this breaks. And resampling seems like it should resolve this, but also it will add in a bunch of noise. And one of the things you want to be careful with when doing mech interp is that you aren't just tricking yourself. Things that involve ablations in the logits are really, really sketchy, because if you've got multiple solutions that all perform well, then first off, they're all going to correlate with each other because they all have big numbers on the correct logits and not big numbers, either near 0 or like very negative on the incorrect numbers. The dot product is going to be a lot bigger than chance, though the incorrect logits are very unconstrained. So the fact that it's in a rank 5 subspace is still impressive. This means that just like if you get rid of everything if there's like 5 solutions of models learned, and you get rid of everything that's like not in one of those solutions, then that's going to do great. Sometimes if you get rid of one of these solutions in a way that adds a bunch of noise, like resampling or something, that will break everything else. In our particular case, I think 0 ablating logits is the most principled.
The sketchy part about 0 ablating logits is 0 ablating logits, as you're saying, works gives high performance as long as you found the correct solution, or like any correct solution,
including a correct solution that isn't significantly learned.
Yes, including one that's not actually the one used by the model. It just happens to be correlated. Yeah. The thing about the resampling ablation is unless you captured all the solutions that the model learns, this is going to significantly degrade performance because you're just going to get like these random noise terms that just like move your model in random directions.
In the same way that, as we'll discuss later, the model needs to stop memorizing in order to be able to generalize. Because the memorizing solution you can kind of think of as a shuffled solution. Zooming out, we've just presented 4 lines of evidence that make us believe we understand what's going on. The bits of evidence were, oh my god, everything is so periodic, what? Then we can just literally read off from the neuron logic map weights what it's picking up in the MLPs, and it's exactly what we expect. Then we can zoom in on specific neurons, and they're approximated really well by these degree 2 polynomials, and they cluster predictably by frequency. We can also understand the attention heads, which I believe one of the appendices goes into in a lot more detail.
Yeah, it's one of the appendices. Yeah.
One of the many, many appendices.
Appendix C1, apparently. Or appendix C something. C2. I don't know, man. There's a lot of appendices.
And then we can check that we're not tricking ourselves by ablating everything that's not predicted by what we're doing, and it's just fine.